Hello folks, today in this video we're going to continue to talk about electrostatics. We're going to take a look at this time at electrical fields and talk about how to calculate them, how to draw them, and then how to imagine the flux through a surface. Let's get started. So we talked last time about electrical forces. Forces describe, literally a push or pull between two charged objects. But electrical fields help us consider what's the effect of just a single charged object on a region of space. So what a field does is some quantity that has a value for every point in space and time. Forces, by the way, don't do this. If you have a positive charge somewhere, you would need to know what's the other charge in order for you to calculate the force between the two. Electrical fields are a way for us just to consider the one charge by itself and what effect it would have on anything in space. So the electric field is a vector field that exists in space produced by the presence of charge. What do we mean by that? What a vector is, of course, is that a vector is a quantity with both magnitude and direction. This makes sense. It has to be a vector, right? Because a positive charge would have a different effect than a negative charge. There would be a directional difference. A positive charge would repel another positive charge, but it would attract a negative charge. And so we have to take that into account by assigning a direction to the electric field. The direction we give the field, by definition, is that it shows or illustrates the direction that a positive test charge would move. What do we mean by a test charge? A test charge is simply us asking the theoretical question. If I put a positive particle there, what direction would it move? Well, because it's positive, and this one is positive, it will be repelled by that and move that way. So the magnitude shows the force on that test charge. In general, the greater the magnitude, the more force there be, and thus the further away it would be pushed there. So that's what an electric field is. Let's talk about how to actually calculate that strength. So the magnitude of the electric field vector, the strength of the electric field, is given the symbol E at any point, and it can be calculated either one of two ways. You can either calculate it by taking the electrical force on an object and dividing by its charge. So if I know that I have an electron here and it's experiencing some force this way, well, I could calculate the electrical strength at that particular point by just taking the electrical field strength, by taking the force and dividing by the charge there. Or I also might notice that I have an equation for electrical force, right? It's K Q1 Q2 over R squared. And so if E is F over Q, then I could just take this equation and divide out one of the Q's. And so I end up leaving me with this. It's K times Q. And we drop the 1 and 2 here because you're just considering one charge. So KQ over R squared. Now, the unit for electrical field vector, there's no, fancy term or a fancy unit. It's just simply the units for force, which are newtons, divided by the units of charge, which is coulombs there. So I want to take my time and take a look at a few different ways that they could ask you to calculate the strength of the electric field. Let's take a look at a few different problems. This first one says the diagram shows a negatively charged oil drop that's suspended motionless between two oppositely charged parallel horizontal metal plates. You're going to see a lot of parallel horizontal metal plates in this class. The electrical field strength between the charged plates is 4 times 10 to the 4th newtons per coulomb. Great. So it tells me that the electrical field strength E is 4 times 10 to the 4th newtons per coulomb. It then tells me that the mass of the drop is 1.96 times 10 to the 15th, negative 15 kilograms. It's being acted upon by a gravitational force and an electrical force. It first just asks me, well, what's the magnitude of the gravitational force on the oil drop? Okay, this is a blast from the past. We've not talked much about gravitational forces in this class, but I know an equation for the force of gravity. You could use the big one with Gm1m2 over r squared, but we don't know the mass of the plates, plus there's the Earth. That gets complicated. Instead, let's assume that this is being done on Earth. We just know that F of G equals mg, where G is the strength of gravity at that particular location. So what I can do, take the mass of my oil drop, 1.96, times 10 to the minus 15th kilograms, and multiply by the local strength of gravity, 9.81 meters per second squared. Calculate that out, and I get the force of gravity at that location to be 1.92 times 10 to the minus 14th Sorry, I forgot my one there, newtons. Then for B, what's this charge of the oil drop? What's the sign and the magnitude? Well, for this, I have to realize that there's a relationship between this force of gravity and this electrical force because this is suspended motionless, which means this oil drop is in equilibrium. There's no net force. Because there's no net force, the electrical force of attraction also must be 1.92 times 10 to the minus 14th newtons. So that oil drop there must be experiencing that force. So then I can find the charge fairly easily. I know E and I know F of E, and we know that E equals electrical force divided by charge. So I'm going to plug those in over here where I have some more space. We'll say that 4.0 times 10 to the fourth newtons per coulomb equals my electrical force, 1.92 times 10 to the minus 14th newtons, and then divide by the charge. And so get the charge from that, and I get the charge of this oil drop to be 4.8 times 10 to the minus 19th coulombs. It doesn't ask me for the sign of the magnitude. I've given the magnitude because I have the size, but I don't have the sign yet. And for that, we have to just think about what's happening with this oil drop. It is being suspended by this force. That force is pointing upward toward a positive charge. If what thing would be attracted to a positive charge, it must be a negative charge. And so that's how I can get the sign of my oil drop there. Okay, so that's one kind of weird application of doing this here. Another thing they might ask is just what is the electrical field strength at distance 2 meters away from a sphere? So they're literally just telling me, hey, you've got a sphere of charge there. What is the electrical field strength right there? 2 meters away. For this one, this sounds, I don't have a force. This sounds like I'm going to have to use that equation E equals KQ over R squared. I know the K, Coulomb constant, 8.99 times 10 to the ninth Newton meter squared per Coulomb squared, and that's always just on your reference table. I know the charge of my sphere, 1.4 times 10 to the minus 6th coulombs. And then lastly, on the bottom, I have the distance, and I'm going to put that and square it. So just 8.99 times 10 to the ninth times 1.4 times 10 to the minus 6th divided by 2 squared. When I do that, I get 3.1 times 10 to the third newtons per coulomb. Then it asked me what force would an electron experience at this point. Well, to connect electrical field strength and force, I can use that other equation, E equals Fe over Q. I know E is 3.1 times 10 to the third newtons per coulomb, but they didn't tell me the charge here. They're expecting you to know, oh yeah, I know what the charge of an electron is. That's one of the elementary charges, negative 1.6 times 10 to the minus 19th coulombs. And I can plug that in and solve for my force, and I get my force to be 5.0 times 10 to the minus 16th newtons. Now, you don't need the negative here. I put the negative in because electrons are negative, but that would just tell you the direction of that particular force here. In this case, it would be attracted to the sphere because the sphere has a positive charge, and so the force will be negative to show that the electron would be attracted that way. Okay, I got one more problem for you. This next one, just to bear with me, this is a difficult one. I would be very, very unlikely to ask many questions like this, and there would be maybe multiple steps, or there'd be things to think about there. But I show this to you to emphasize the point about this being a vector field, because vectors don't work exactly like we want them to often. So I'm going to draw a little picture here. It says consider two charges on a line. So each charge has a magnitude of plus 4 microcoulombs, and they are separated by a distance of 2 meters. It wants to know the direction and magnitude of the electric field strength at a point 2 meters above the line, directly between the two charges. So if I imagine drawing a line up here, here's my point P, and that is 2 meters long, and these are 2 meters wide, so there's 1 meter to that point right there. I want to know the magnitude and direction of the electric field strength at a point 2 meters above the line. So here's where I'm going to do first. Let's just figure out the electric field strength from charge, we'll call it charge 1, and from charge 2. So let's do 1 first. Well, 1's pretty easy. I can do E equals K Q over R squared. I just need to know the distance to point P. Well, I've set up myself a little diagram here because you might have done this before. I'm going to need to do a triangle here. And so I need to figure out what the side length is here. Well, I can just use, because this is a right triangle, the Pythagorean theorem. 1 squared plus 2 squared is 5. That's going to be that distance squared. So that's going to be square root of 5. So that'll be that distance between the charge and point P. And that's what I need to use in my equation here. So I'm going to plug in K, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, times Q. Q is 4 microcoulombs, so 4 times 10 to the minus 6th coulombs, because 10 to the minus 6 is what micro means, and then divide by the distance, square root of 5 squared. So pull out your handy dandy calculator, multiply the top two numbers together, and then divide by the square root of 5 squared, which is just 5, and I get a value of 7.2 times 10 to the third newtons per coulomb. Okay, we're going to deal with the direction in a second, but that's my first one. Let's make this one pink then. Number 2. If I wanted to do number 2, hopefully you can see, I try to make this easy, that I'm going to be solving out the exact same problem because it's the same charge and the same distance away from point P. So if you'll allow me, this is definitely just the same thing. 7.2 times 10 to the minus third newtons per coulomb. And then I'm done. Okay, that made it pretty easy then. I know the electrical field strength due to each sphere there. Now what's the total? Well, it would be convenient if I could just add these two numbers up, but I can't. And that's why I'm showing you this problem. The problem is that these things are vectors. So if I consider this 7.2 times 10 to the third newtons per coulomb from the first charge, right, it always points away from a positive charge. So it's going to point this way, and it's going to have a value of 7.2 times 10 to the third. And then the pink one is going to point this way, and it will have a value of 7.2 times 10 to the third newtons per coulomb. I cannot just simply add those together because they are vectors. If you remember, you have to add vectors either tip to tail, or you can add them by components. So I'm going to go ahead and show you what you would do to add these two here. Though this is a little tricky, but bear with me. What I'm going to do is I'm going to find the components of these two vectors. I want to find out what is the x component and the y component of the electric field strength for each one at that point there. So to do that, I need to find these two sides, and to do that, I need to find that angle. I did not draw this very well because I am terrible at geometry, but if you will bear with me, that angle and that angle are the same. I know they don't look like it because I didn't draw this very well, but they are definitely the same. So to find that angle, I just need to I'll do inverse tan of 2 over 1. So inverse tangent, I'll make sure I'm in degree mode here. Inverse tangent of 2 over 1. And I end up getting 63 degrees. So this, draw it out yourself if you'd like. You can show that that should also be 63 degrees. And so then what I can do to find the x component of this, that's just going to be the cosine of this angle, because this is the adjacent side. So cosine of 63 times that value. So 7.2 times 10 to the third. And when I do that, I get a value of, should take the cosine first, 63 times 7.2, 10 to the third. I get 3.3 times 10 to the third newtons per coulomb. So that's going to be my x component. To do my y component, I would do a similar thing, just with the opposite side of that triangle. And to do that, you would use sine. So sine of 63 times 7.2 times 10 to the third is 6.4 times 10 to the third newtons per coulomb. Okay, so I now know the values of the x and the y component of those there. Then we have to make another argument. The other argument is, what are the ones for this one going to be? Well, because they're the same value. And if you do this math, that is also 63 degrees. So that's 63 degrees there. If you do the math, you'll find out that the x component of this one is the same value, just in the opposite direction, because it would be pointing that way rather than that way. So I'm going to call it negative 3.3 times 10 to the minus third newtons per coulomb because it's the opposite direction. And the y component would be the same value because it's going to be still up. Okay, after that, I can now kind of use some algebra and some thinking about vectors to find the total. I know that this one is the same value, but the opposite sign of the x component of the other one. So these two are going to cancel out. There will be no net x component to this electrical field strength. And then to find the total upward, I simply need to add the y components of those two vectors. So 2 times 6.4 times 10 to the third. So 2 times 6.4 times 10 to the third is, I'll call that E total, 1.3 times 10 to the fourth newtons per coulomb. And that would be in the upward direction to figure out the direction there. Whew. Okay, so how to summarize all of this? First off, note that if you have 2 or more charges, you can find the electrical field strength at a particular point away from those by simply adding up the electrical field strength due to each charge. So the first step is to find the one for charge 1 and for charge 2. But when you add them up, you have to remember that they are vectors. So you cannot just add the values. You have to take into account the direction. Here we used a component trigonometry argument. You could do some other things if you want to do it graphically with tip to tail or any other way that you know how to add vectors. And then we found the net electrical field strength and expressed it as a magnitude and a direction. Whew. Okay, that's been enough about electrical field strength. Let's go ahead and take a look then at some depictions of the electrical field. The way we depict the electrical field is using electrical field lines. We've kind of been dancing around the fact that we show these as arrows. And so a positive charge or a negative charge would have some arrows around them to show which direction the electrical field is pointing. Some key rules about electrical field lines. They always point away from a positive charge and toward a negative charge. The way I remember that, as I say, in physics, we think positive. So away from positive. Positive always is first. We think positive. So away from positive and toward negative. The next thing is that the density of field lines is proportional to the charge. What I mean by that is if you had a charge that had less positive charge than this one, you would maybe draw less field lines in the same amount of area. There's less field lines, thus it is less of a charge. The next and last point is field lines can never cross. If I were to draw field lines between two charges like this, I'm going to start on a positive and end on a negative. I could draw them like this here, but I could not draw one like this. The reason being that these field lines show me what direction a charge will move, right? If I have them cross, which way is a charge going to move there? What it's telling me is it's going to move 2 different directions. That's bad. That will never happen. Charges do not move in 2 different directions at the same point. So we know that field lines can never cross. So that's my rule, our rules for field lines. So given these field lines above, what do we know about is true about A and B? Here's a little example problem for electrical field lines. Well, remember, in physics, we think positive. So we start on positive charges and end on negative because these electrical field lines start on A and B. We know that both A and B have a positive charge. You also could figure out one other thing, probably, which is that A and B probably have the same charge because they have the same number of field lines leaving both of them. Okay, last question about electrical field lines here. What is the charge, it says here, of plates A and B? And then draw a field line between A and B. And one thing I didn't say in this is that this would be told to you in the problem. That's showing you the direction of the force on the electron. So an electron is feeling a force toward plate A. So if an electron is feeling a force toward plate A, that means that plate A must be positively charged and plate B must be negatively charged. And if I were to then draw a field line between the two, I always start from positive and go to negative. And so I could draw them down like this. Leads to the key point that a negative charge goes backwards on field lines. Remember that field lines are defined to show you the direction a positive charge would move. And so an electron or any other negatively charged particle will go opposite the right direction of the field lines. Okay, guys, thank you for bearing with me. We have one more concept for this one, and then we'll be done for the day. That last concept deals with flux. So before we get to flux, here I just want you to have in your notes these two drawings here. These come up all the time. They are the electric field line diagrams for a dipole. What's a dipole? Dipole is simply a configuration of charges that have two opposite charges or two similar charges, any two charges, either two positives, two negatives, or a positive and a negative. So these pictures come up quite a lot. Okay, flux. What electrical flux is? Electrical flux is a measure of the amount or the net electrical field going through a defined surface. So electrical flux measures how much electrical field is going through a surface. In a way, you can think about it like measuring that amount of charge that's producing this electrical field. It's a way to measure the amount of lines going out of there. Now, you can think about flux that way. In two different ways. It either tells you how much charge is enclosed in an object, or it tells you the electrical field strength flowing through a surface. So we have two different equations to calculate electrical flux. Electrical flux is given this strange symbol here, which is the Greek letter, capital Greek letter phi, and it is either equal to Q enclosed divided by epsilon naught, or it's equal to AE cosine of theta. Let's walk through each of these equations separately. The first one, Q enclosed, what that means is that if you have some configuration of charges, let's say you have a +1, a +2, and a +3 charge, and I draw a surface around those charges like this. I could calculate the flux through that surface by simply adding up the amount of charge enclosed and dividing it by this number. So I could do flux is equal to the total charge, which would be 1 plus 2, 3, 6, divided by epsilon naught. What's epsilon naught? Epsilon naught is a number related to the Coulomb constant. Epsilon naught is the technical value of the permittivity of free space, but you should know it's a number. It's 8.85 times 10 to the minus 12 coulombs per Newton meter squared. So I would put that on my bottom here, though I didn't define these are, let's say these are all coulombs. So that's coulombs, then 8.85 times 10 to the minus 12 coulombs per Newton meter squared. Divide those out and you would get a value for that flux. In a way, it's measuring what's the amount of field lines, leaving this surface and going through it there. The other way I could calculate it is if I had, some external electric field. Let's say I don't know what charges are making my electrical field. I just know my electrical field looks like this. Well, this equation is useful if I just say, I want to do that in red, here's my surface. What is the flux of lines through that surface? What you need to know, A is the area, the surface area of that surface. E, of course, is your electrical field strength. And then cosine theta, my theta here is what is the charge, sorry, not charge, the angle in between the electrical field and the line perpendicular to that surface, otherwise known as the normal line. So why is that important? Well, that's important because if you consider a different way of arranging these charges here, let's say I had my electrical field going this way. And then let's say I drew my surface like this in blue. That's my surface. There are no lines going through that surface. Why? Because the angle in between the normal line and the field is 90, and the cosine of 90 is 0. So this captures the fact that there would be more flux if it was completely perpendicular, and no flux if it was completely parallel to that electrical field there. Okay, let's take a look at some examples, then we'll be done for the day. So the first one, a uniform electrical field with a magnitude of 400 newtons per coulomb is incident on a plane surface of area 10 meters squared. It makes an angle of 30 degrees with a line normal to the surface. What is the electrical flux through this surface? So I got to, with these electrical flux questions, just figure out which equation am I working with. Is it the Q enclosed one, or is it the with the angle and the area? They make this one kind of easy because they've mentioned the area and they've mentioned the angle here and the electrical field strength. So I know what equation I'm using. It's going to be flux is E times A times the cosine of my angle. And so I got to plug in my numbers here. 400 newtons per coulomb is my electrical field strength. A is 10 meters squared. And then it's the cosine of the angle, 30 degrees. So grab out your calculator, make sure you're in degree mode. 400 times 10 times the cosine of 30. And I get a flux of 3,464 Newton meters squared per coulomb. Okay, last question here. A proton sits 2 meters away from a neutral conducting net metal sphere. What is the electrical flux through the sphere? Okay, so I've got a sphere here, and I know that there's a proton a couple meters away, wants to know what the flux is through the sphere. I use this example because it helps illustrate two things. First, from an easy perspective, I got to figure out what equation to use. I don't know, and I guess I know the angle, but I don't know the area of the sphere. And I don't know I guess I could calculate the electrical field from the proton, but I don't know the area of this sphere. So I'm probably not using that equation we just used. I'm probably wanting to use this equation, Q enclosed divided by epsilon naught. And I can take this literally. How much charge is enclosed by the sphere? Well, there are no charges inside the sphere. So, as you can imagine, this one is kind of a trick question. The flux is zero. But I use this to illustrate at a really important point. Why? Why is the flux zero if there's no charge in the sphere? Because if you drew the field line coming from this proton, it would go into the sphere this way, and then out of the sphere on the other side. So on a whole, there's just as many lines going into the sphere as there are lines going out of the sphere. And flux is a measure of how many electrical field lines are leaving this surface. Since there's one in and one out, the net is zero. That's why it's just based on the charge enclosed. It does not matter how many charges you put outside this sphere, the net will always be zero. Okay, folks, that is it for this video. Thank you guys so much for watching. Have a fantastic rest of your day.